Welcome back, ladies and gentlemen, and welcome to ICEM 2021. Our sponsor will begin now. Please be advised to stand by. Ladies and gentlemen, we're honored to have Mr. Leong Moon Kit, Territory Sales Manager of Oxford Instrument Nanoanalysis in the sponsor talk. Mr. Leong Moon Kit will deliver a talk on EDS characterization for lithium-based battery material. If you have any questions, please send your questions to the presenter via the Q&A function in Zoom or the comment function in YouTube. All questions will be addressed by the end of the presentation. Hence, I would like to remind Mr. Leong Moon Kit to look at the Q&A function if there are any questions coming from the viewers. Please welcome Mr. Leong Moon Kit. Thank you.
Hi, good afternoon, everyone. So this is MK Leong, so representing Oxford Instruments to giving this sharing session for this this conference. Okay, it's our great pleasure that is being invited to joining this ICEM. Okay, so I guess we are going to start in a short while, right?
Mr. Leong, you can start now.
All right, okay. So just to confirm again, is it anyone, you can see my share screen now, the slides?
Yes, it's very clear.
Okay, so very good afternoon to everyone, all the participants. And again, I'm K Leong from Oxford Instruments, and it's our pleasure to be invited in this event to sharing some of our latest technology or some of the solutions regarding on the battery solutions. Okay, 1 second. All right. So before I start, today's in this short session, I will mainly sharing on the Oxford Instruments product for the battery industry. So there's actually quite a wide solutions that the wide range of the solutions provided from Oxford Instruments, but today I will just sharing just part of it, just in case you're interested on some of the part, or there's something that I do not share out, just please feel free to drop me an email. So later part I will share out my email as well, my contact. All right, so before we start, then I just have a very short introduction about Oxford Instruments. So actually Oxford Instruments is a worldwide scientific equipment provider, and also the science and technology equipment research solutions provider. Okay, as the name itself, Oxford Instruments actually is a spin-off from Oxford University, okay, back to like around 35 years ago. So in our side, Oxford Instruments, we have a multiple business division, and of course, mainly are focused for the industrial, in semiconductors, a battery, and research market. Okay, so just some general overview for the company. So actually, currently, we are looking at Oxford Instruments looking at the last financial year revenue rate around 317 million pounds. And of course, because we are one of the leading technology solution provider, we are spending like more than 8% of our revenue invested in R&D and the development of new product and technology. So later part, I will share with you some of it, including some of our highest and EDX analysis solution that are available in the market now. All right. So worldwide presence, we have like around 28 to 30 offices worldwide, covering over 18 countries, around like 1,600 people worldwide, including the R&D manufacturing, and also sales-based, just like myself, and also the marketing in both Europe, North America, and Asia. So of course, over here, not only the sales side, we also have a global distribution and technology centers, which are the technical team and also the research scientists available. So the nearest one we have in Singapore and also China. And of course, some of the customer having a very stringent or very critical processes in industrial, such as like data storage, like hard disk manufacturers and semiconductor microchip manufacturers. We're also providing the 24-hour service support. Okay, so this is an overview. All right, let's get to our topic today. So generally, these are the solutions that are available from Oxford Instruments for the battery industry. So basically, I think for our side today, because due to the time constraint, we will focus on the first part only, which is the SEM-based tool, which is the EDX. And of course, SEM-based tool, as you've seen over here, not only the EDX, we also have the stack wave, which is the quantitative analysis for trace element by using the WDX. And of course, another one, which is a HKL and the crystal, which is focusing on the EBSD, electron beam diffraction. And of course, on the higher end side, we also have a solution based on the focused ion beam, which is using the Omni probe for the electrical characterization or the current characterization. Okay, and besides only SCM-based tools, I guess later part we will also have another business division. We share with you another solution which is more on the NMR side. And yesterday, my colleague also shared you on the AFM side. And on top of that, some of the solutions are interconnected, just like the AFM. We have another solution that to do the correlation between the SCM or TEM together with the AFM. We call it a relate. So it's a multi-technique data correlation. So imagine you do an imaging or characterization in SCM, but however, we know that SCM mainly are the 2D the topography imaging, and unlike AFM, we can go for the 3D characterizations. So we can do the correlation between the samples, images, or the region of interest. Okay, back to our part, which is the SCM-based tool. Today, in this part, I will share with you mainly on the field of the very first part of it, because as you've seen over here, probably it's a little bit long process, the battery manufacturing process from the mineral itself, the raw material exploration, until the mining process and the raw material processing, of course the component manufacturing and electrode anode and electrolyte, and each of the components and the raw material QA, QC, and of course the later part on the battery assembly and the QA, QC for the final product. So because of the time constraint again, today I will just share with you on the first part of it, which is mainly on the characterization on the raw material itself. In the short one is like the powder or the raw material characterizations solution that we have. Just in case you are interested on some other part of it, you may just drop me an email or questions later. I can share with you in further information. So for the SCM-based analysis during the manufacturing process, actually we can divide it into two application areas. Of course, the first one will be the cleanliness of the product's powder. Okay, typically it will be like the entry-level SCM. The WCM is the tungsten SCM, and of course there is also a TTM, which is a tabletop SCM as well, and a simple EDX or the features analysis. So later part, I will share with you a little bit more detail on this EDX and the features analysis. So what is it about and how is it this solution can help you in terms of doing the characterizations and the qualification of the samples, the raw material itself. And of course, the second part will be more on the R&D failure analysis. But over this part, I will not really touch on it. I just share with you most of the one of the application example, because the whole process itself actually is a quite a long explanation on this. Okay, all right. So powder cleanliness for the electron manufacturing. So in this case, we have a solution. We call it an Aztec battery. So for all of our Oxford Instruments EDX, WDX, and EBSD solutions, we operate under the same platform. We call it an Aztec platform. So within the platform, we have a different solution. So in this case, we are sharing you the Aztec battery just in case you're interested on some other solution like the metallurgy solution. We have Aztec steel, or you're particular in the mechanical parts cleanliness characterization. We have Aztec clean. This one is targeted for automotive application. So over here, I just share with you on the characterization on impurities and the contamination by using the Aztec battery and our EDX. Okay. So the requirements, just an overview. The requirements for the powder analysis, what is it we need it? So we need a reliable, precise, and accurate EDX measurement to measure some of the particle morphology and also the size. And of course, most important is the composition of the compound itself. So each of the compound, imagine you have like several grams of the certain amount of your sample in the powder form, which consists of probably hundreds until more than hundreds, thousands of the powders. We need to classify it, or we need to characterize it, each of the particles, and to separate it and detect the common contaminants. So imagine there is one without the automated solution, the user or the researcher or the QC officer, they need to manually detect, to do the EDX analysis manually. So this is a lengthy and a very tedious process. So for this case, Aztec battery offers the total automatic particle characterization, so which is targeted for this application. So on top of that, after that, the characterization, we have a particle relocation and correlate with the image that we capture from the ICEM, and from there, they correlate each of the particle with the specific the element that contain on that particle, and we can do the reacquisition on the spot, providing we doesn't move the sample, because the SCM stage location is registered into our system, the software itself, so we can recall and locate that particular particle or the contaminant. So system validation, which is a routine workflow that to confirm the optimization and the standardization of the parameters of the characterization, like the KVs and also the working distance of the SCM. Okay, and just to maintain the stability of the system and the so-called routine parameter, everything is standardized. And of course, the high sample throughput due to its automated analysis. So the user doesn't need to sit in front of the system throughout the whole process. So typically, let's say we have like more than 5,000 of the particle to be analyzed. We doesn't need to sit in front of the system itself. So we just set it up and then let the system run it. And by end of the analysis, then we can just capture and also extract the data. All right. So next, Aztec battery is just like I mentioned before. Aztec battery is one of the features, Aztec features sub application software that is optimized with the special or the standard protocol, and also the database targeted for the batteries material. So what we need, what we use it by the user profile, we can set the image acquisition condition, which is on your SCM side, like the KVs, like the field of view, or the location of the characterization. Okay, and acquisition conditions, yeah, just I mentioned about, includes the powder or the raw material classification scheme, because we understand that some of it, different manufacturer or customer or even researcher, they have a different kind of raw material mixture or recipe that they want to do the characterization and do the comparison. And all of this, we can set it in a different classification scheme. So of course, most important is including the dedicated step notes. This is something like the user guide for a multi-user environment. So this one is more on the operation sides. Okay, so who will be using, or who is find that this application software is useful is a customer performing analysis for the battery products, which is a manufacturer, and the manufacturers for the precursor materials for the batteries, and of course, not limited to that, and of the raw material mining and the raw material suppliers to qualify all the incoming QC for the raw material itself. Okay. So this is how we get it, and in terms of the results and the characterization, SCM provides the imaging for the small particles, and of course, we can do a simultaneous collected information for the particle morphology and the composition elemental or the chemical composition. And the main advantage over some other techniques, or I would say not over the advantage over some other techniques, is can be complementary to other techniques such as ICPMS. We can simultaneously acquisition of the particle image and the composition information, and fast, efficient acquisition setup. Unlike the spectrometry, we need to dilute or break down the sample into a very small percentage or a very precise amount to do the characterization or the quantification. Over here, for SCM and DDX, we can put the sample as it is. So we just directly put the powder onto the SCM stop just to fix it, then put into the SCM, we can start the analysis. Okay, and of course another one, most of the researchers that they like is a non-destructive methodology to do the characterization, and of course this is a repeatable and of course a widely accepted QA and QC protocol, and versatile because our site is providing a solution. Our solution is like compatible to all microscope. I mean, in this case, it's electron microscope types, or doesn't need to have a specified brand or certain fixed model of the SCM is needed. So on the market, all the major SCM manufacturers or the major SCM brands are compatible with our system solutions. Okay. So now we're going to slightly more detail. We are looking at some of the example of the so-called, the contamination of that raw material, okay? So by using the Aztec battery. So this is an application example. The problem is that, I guess if you still recall some of the news back to a few years back, I guess. Okay. There are some short circuit, or make it simpler, the battery is exploded in some of the major cell phone manufacturer. So this is some of it. The problem is to identify the metallic contaminants that introduced during the raw material blending, and where some of the raw material, there are some contaminants that induce or cause the short circuit, and further that resulting the battery itself exploded. So what we have is we want to avoid this kind of accident happens. So what we need to do is we provide the solution from manufacturer to do this analysis in the raw material stage to identify there's any possible foreign particle or contaminants that will cause this problem. So from there, we develop this system, and further on this so-called the raw material characterization workflow. Okay. Next, okay. The lithium battery consists of different parts. So as we know, it's the cathode, anode, and the electrolyte, and of course the metal connection between the cathode and anode. In this example, where we share with you, focus on the cathode material. However, this example is not limited only on this cathode material, but it's also covering two other parts in the manufacturing processing. Okay, the cathodes are typically made from a mixture of the metal oxide powder. Generally, it's the cobalt oxide and also the manganese oxide. So it is very crucial that the manufacturer or the incoming quality control to make sure there is no other so-called contaminations, especially the metallic contamination that will cause the failure. The so-called contaminants, it can be induced during the processing, it can be during the crushing on the mechanical parts, like the alloy fragments from the machinery or the packing. It can be from all sorts of the possible source or during the process. And in this case, we show you one of the examples, relatively large metallic particles that can induce the short circuits within the battery itself. So this is quite crucial. So we are looking at the cobalt oxide potential contamination by the silver, copper, and zinc particle. So this one, in this example, the particle size is like around 1 micron. So typically, if you imagine you have one batch of sample, just probably like less than like 1 microgram or probably like 10 microgram of the powder, the raw material. We are looking at this kind of small powder. Under SCM, we are definitely do not have any way to separate it or identify which of this powder are the contaminants. Because as you've seen over here, it's like a typical SCM image with the powders. It's quite well consistent in terms of the sizes and the shapes. However, we still not able to identify which are the contaminants material, even though inside for the SCM, we can use the BSE detector to detect the particles or the morphology of the features by the atomic contrast. In this case, it's mean the higher the atomic number, the particle or the features appears in this image will relatively brighter. Okay, so typically, if you are familiar with SCM imaging, for normal topography imaging, we are using a secondary electron imaging. Okay, so this is how we the material looks like inside the SCM under the SCM imaging. Okay, so in the past, the conventional way, the characterization need to be done manually by the operator. Manually spot the contaminants particle to that, then further to put it into the EDX to do the analysis to identify it. So this one is relatively rely on the experience of the operator itself. So some of the operators or the officer, they are very experienced. From a glance of the image, they know that, okay, which one is the contaminant. This one is, everything is based on experience. If imagine there is a new engineer or new personnel joining that company to take over the QC part, then the experience is not that much. You may miss some of the crucial, important features that may be contaminations. So in this case, what we have is by the Aztec features and the Aztec battery application software, which is automated software, you can teach the software itself to do the particle analysis on this specific field of view, to do the analysis, EDX analysis, each of the particle by itself. And of course, by the mean of analysis, it's not only taking the photo or the ICEM micrograph of that particular particle. In the same time, each of these particle will be analyzed by the EDX. In this case, you see that there's some colors over here indicate the types of the possible content on that particular particle or the features. And from there, each of these features will be recorded in the software results, and the user can create the one whole list of compile the whole list of the example and just glance through, see which are the particle is the foreign or the contaminant particle, because each of the particle is being analyzed by the EDX. And when we in the software, when we click each of the particle, it will shows up this spectrum. In this case, you can see that the features or the particle number 4074, that in this example, this area with this particular spectrum. Okay, so this is how it looks like in terms of the operational. So its advantage is to minimize the human error during the operation and the characterization, and also shorten the time of the analysis, and of course push up the throughput. So this is the analysis algorithm by using inside our software, which is the Aztec TrueQ. Okay. So this is what we look at. We can do the typical reliable detection with the auto ID from beryllium to americium, but however, later part of it, I can share with you another new type of the EDX detector, which probably may give you some idea, okay, what can be done. Okay, so spectrum convolution, back to here, and the background subtraction. This is the standard algorithm that our Aztec TrueQ using to do the characterizations. All right, next. So another example is that just to show you, which is the analysis of this solid state granite electrolytes. So typical composition is this. There's consists of lithium, platinum, zirconia, and oxygen. So by default, this compound is made up of two different phases, which is the lithium aluminum oxide and the lithium platinum zirconia oxide. So when exposed to the air, it will form a lithium carbonate, I guess, and also out of the lithium aluminum oxide phase. Okay, so the challenges of this analysis is that the battery material, this raw material, is very beam sensitive. If you are not sure, not familiar with ICEM, in this case, we mentioned about the beam sensitive sample is that, imagine when we are doing the analysis in the ICEM, we are physically bombarding the sample surface with an electron particle, and then from there, the electron particle will generate or excite the electron signal from the surface, the sample surface, and generates the secondary electron and the backscattered electron SE or BSE signal for us to observe the topography or the so-called compound, the elemental contrast of your sample. So over here, the battery material often contains the light element. In this case, typically is the lithium, which is very sensitive. The material cannot withstand a high dosage of electrons, and it will break down or degrade if being radiated for a long time. Or in other words, is if we keep on imaging on the same area of that particular sample, it will degrade, or a simpler word is that the sample will be damaged. So to let you have a visualization of this sample, how does the sample get damaged by the electron beam, you can see that. So this is one of the particle, consists of the lithium compound. And even though for those researcher or you guys are familiar with EDX operation, typically we are using around 10 kV or maybe 15 kV, even 20 kV to do the EDX analysis. This is most common setup for the EDX analysis. However, for those beam sensitive samples, even we put it at 5 kV, as you see over here, it's also strong enough to damage the sample. As you see over here, before the analysis, just the first snapshot of the image, you can see that the sample itself, it looks relatively clean. And after some time, we keep on imaging on this sample, and then you can see that there's a form of a lot of the small particles is formed. That is the lithium oxide on the surface. So this is one of the commonly observed beam damage, electron beam induced damage on the sample surface. So how are we going to overcome this? Is we use a very low kV analysis. Okay, before we go that, just to share you some of the example again. By 5 kV analysis, after 10 minutes for the map acquisition, the EDX mapping with a 500 picoamp beam current. As you can see that we got the sample itself, the result looks, well, not too bad. We can get all of the material inside here. We have detected all the compound inside. Okay. Those by using our auto phase, the phase characterization, the system itself, they can identify both of the phase over here. However, after the acquisition, you can see that there's a lot of small particles suddenly just shows up. So this is the typical the so-called the grain damage induced by the electron beam. Okay, so you can just try to remember this EDX mapping. So confirmation is not a problem. And then, but however, the sample has suffered a significant beam damage, and the X-ray map is no longer reflective the elemental distribution in the sample, because after the damage, you can see that a lot of the lithium oxide is formed on top of the surface. So if you said you want to do another round of the analysis, or you subjected this sample to another different methodology, it will be not representative for this particular area anymore. All right. So next, the same sample but different area, we subjected it to under 2.5 kV analysis. So if you operate the EDX and ICEM before, most of the time you will know that any EDX analysis below 5 kV, it will be unlikely or near to I would say near to impossible to be done. But however, for Oxford Instruments, we have a very different kind of technology, different EDX detector. Later part, I will share with you what is the detector name. So that before that, I just share you how does it look like. By reduce the time of the acquisition and also the beam current. Just now we are talking about 500 picoamp with 10 minutes. And now we are talking about like 7 minutes with 100 picoamp of the beam current. So the dosage, the electron beam dosage is significantly lower. And as you can see that, if you are using SCM before, all of us know that the lower the kV, sometimes it will produce relatively higher in terms of the spatial resolution. Therefore, you can see that the features itself is significantly clearer in this EDX mapping. At the same time, we're still able to capture the compound of the material itself. And after the acquisition, yes, you can see that the contamination or the beam damage, electron beam induced damage is much lesser. Even though you can see that you can refer to this area. Initially, we only have like one big particle on this side, but after 7 minutes of the analysis, yep, there's a little bit of the damage over here, but compared to the previous one, you can see that the damaging or the so-called the beam induced damage is significantly lower, or I would say probably near to negligible. So this is the advantage that we, or the advantage technology that we have to allow us to do the very low kV EDX analysis, especially for the beam sensitive material. Okay, so to confirmation element, we're using a sub 1 kV X-ray line, which is over here, this spectrum. So typically, this is we are referring to the platinum N line, zirconium M line, aluminum L line, and the lithium K line. So, and then I just want to mention a bit, a very little or negligible beam damage we observed from here, and the analyzed sample is the sample itself doesn't damage. Okay, so this is how does it looks like even after three analysis over here. Okay, and you may ask that how is it the software itself can do the separation or identify the three phases. But this one will be another subtopic on our software application. So over here, I just briefly to let you know that we have the solution. We call it Aztec phase, okay, auto phase analysis. So they can do the phase separation by using this true map, okay, to separate the lithium K line from the aluminum L line to show the exact or the true distribution for the material that who are in overlapping. Okay, not limited to the lithium K and also the aluminum L. There's some others as well, like silicon and also the tungsten as well. Okay, so this is one of our special so-called technology. Okay, next moving. So the lithium battery design in current generation route by using the graphite anodes, and of course in the lithium battery cathodes with transition metals oxide. Okay, these are some of the compounds, and probably if you after seeing the previous application, when you ask that, is it something not right about the EDX analysis? Because as you understand that there is a limitation in the EDX detection based on the theory. So you may ask that, based on what we understand, the lowest and the lightest element that we can EDX can detect, it can be from beryllium at the moment. But however, how is it we able to detect down to lithium, which is the so-called atomic number 3? So later part I will share with you on this. What is the detector we use? Okay, so just to share with you, there is no lithium X-ray or the EDX detection from the material by any others method, any others manufacturer EDX, or even a small angle. Okay, so so this one we put aside first, and the next generation material, we have like the lithium compound, which is a lithium sulfide, and the silicate or borates. And in the garnets, we also have this compound consists of the lithium and lithium polymer and the lipons. And we can show you some of the example that our detector able to detect the lithium. So this is one of the small particle, but over here, we just to share with you, we can also do the nano characterization within a high speed collection. So this one is not a TEM image, but this is a SEM image. The particle itself is 25 nanometer, real-time data processing of very low kV spectral data. So So it's collected at 3 kV, 4 mm working distance for 22 minutes under 15,000 counts per second. This is a very low kV and low dosage EDX characterization, but we still can get you can see that the nitrogen is detected and niobium and also the aluminum oxide. Okay, as you can see that the center particle or the core itself. Okay, and on top of that, not only nitrogen, and you can see that we can separate it out, the nitrogen and the titanium overlapping. We can separate it out over here. The oxygen and the chromium as well, overlapping. All right. So next, I would like to share with you on this, the ultra extreme, which is our highest end EDX detector that available in the market at the moment. So this is what we have to share with you. The typical particle analysis is around 20 to 30 nanometers. Okay, the most sensitive STD detector available in the market.
Hi, Mr. Leong. Sorry for the interruption.
Right.
Probably you can wrap up because we have the plenary speaker at 2 p.m.
Okay, sure.
And the plenary speaker is coming from Germany. He's actually in the floor 25 minutes before this session. Thank you very much for your attention. Thank you.
That's okay, no problem. All right, so get back to here. So this is the highest end detector that we have. So moving forward. Okay, so this is the detector itself, which is ideal for the low kV analysis, especially on the beam sensitive material. And from here, that are the detection that we're able to do it under 3.5 kV analysis. And just to show you, at 5 kV, the NCA cathode, you can see that the mapping looks not too bad. However, you can compare it. The higher kV, the spatial resolution is lesser. So what about TEM level? By using the ICEM analysis, the cobalt-rich core shell structure over here. So this is another results show you. And yeah, these are the two applications I would like to share with you. So from this, I will end my part over here. And as you can see, we have the whole complete analysis for ICEM solution, the EDX and the WDX, and also the EBSD. So if you have any further question from after this, please feel free, you can just drop me an email over here. This is my email, or you can visit to our website. There is a lot of the application notes and different kinds of research results that we shared out, as well as the recorded webinar and tutorial. Okay,